Hello everybody, good morning. Myself, Dr. Shubhankar Sen, an Associate Professor in the Department of Mechanical Engineering, IIT ISM Dhanbad, welcome you to the first lecture of the 8th module of the 12-week SWAYAM NPTEL course, Finite Element Method in Thermal Engineering. In today's class, we shall illustrate the Galerkin finite element discretization of the unsteady convection diffusion equation in one dimension. In the 7th module, we started with the finite element discretization of the marching problems. In module 7, we discretized parabolic and hyperbolic partial differential equations. For parabolic PD, we considered the transient heat conduction equation, it was del T equals to alpha del square T plus S tilde. Here, this was our unsteady term. This was the diffusion term. And this was the source term. For this case, there is no convection term and we did not get any convection matrix. We got only diffusion matrix, which we denoted as the stiffness matrix. So no convection matrix. Next, we considered hyperbolic PDs. Two types of equations we considered. First order wave equation, del U del T plus C del U del X equals to source term. In this case, we have convection term, but we do not have any diffusion term. So first term is unsteady term. The second one is convection term. The last one is the source term. So in this case, we got convection matrix, capital C, but no diffusion matrix. Finally, we showed the semi-discrete form of the second order wave equation. So second order wave equation, del 2U del T2 equals to C square del 2U del X2. So the left hand side represents the unsteady term. The right hand side represents the diffusion term. So in this case, we had no convection matrix, but we had a diffusion matrix. No convection matrix. We had diffusion matrix for this case. So these are the three different types of marching problems that we have discussed in the 7th module. In today's class, we shall begin with the convection diffusion equation, where the convection and diffusion, both terms are present in the governing equation's strong form, and because of that, we shall have both the convection and the diffusion matrix. So let us consider the convection and diffusion transport of a property U in one dimension. The unsteady convection diffusion equation is given by del u del t plus c del u del x equals to nu del 2u del x2 plus the source term for x varying between 1 and 0, for example. So here the first term, it represents the unsteady term. The second term represents the convection term. The third term represents the diffusion term. And the last term, it represents the source term. Here, C is the convective velocity. We consider the convective velocity to be a known quantity, and because of this, the convective velocity portion or the convection term is acting as a linear term instead of a nonlinear term when C is substituted by the unknown quantity U. Here, C del u del x is a linear term with C acting as a coefficient. Nu is the diffusion coefficient for the transport of U. So we can write the strong form of this equation as the strong form of the above equation may be rewritten here. Find U, the degree of freedom, such that del u del t plus c del u del x equals to nu del 2u del x2 plus sx for omega into the time domain. Here u is a function of both space and time. We consider two different types of boundary conditions for this problem. We consider u equals to g on gamma g. This is the essential boundary condition. And then we consider nu du dn equals to h bar on gamma h. So these are the two boundary conditions possible. One is of essential type, other one is the NBC type. So the first one is EBC and the second one is the NBC. So now we derive the Galerkin weak form for the problem. Let us derive the Galerkin weak form using the statement of method of weighted residuals for a finite element omega e. The integral form may be given as integration over omega e. Weight function is a function of coordinate and residual is a function of both space and time. D omega E equals to 0. In this case, our residual Rxt equals to del U H del T plus C del U H del X minus nu del 2 UH del X2 minus Sx. The integral form reduces to integration over omega E Wx into del UH del T plus C del UH del X minus nu del 2 UH del X2 minus S d omega E equals to 0. In one dimension, d omega E is dx. We simplify the above integral form by dropping the superscript h as integration over omega E w del u del t plus c del u del x minus nu del 2u del x2 dx equals to integration over omega E ws dx. Separating the terms containing w and u and terms containing w only. From here we get integration over omega E w del u del t dx plus integration over omega E w c del u del x dx minus integration over omega E w nu del 2u del x2 dx equals to integration over omega E w s dx. Now we perform the Green-Gauss integration for the diffusion term that is appearing in the left hand side now. Use Green-Gauss integration to get integration over omega E w del u del t dx plus integration over omega E w into c del u del x dx minus integration over omega E nu into gradient of w dot gradient of u minus dx plus boundary integral along gamma E nu into w del u del n d gamma E equals to integration over omega E ws dx. This can be simplified as integration over omega E w del u del t dx plus integration over omega E w into c del u del x dx plus integration over omega E nu into gradient of w dot gradient of u dx minus boundary integral along gamma E w into nu del u del x d gamma e equals to integration omega e ws dx. In one dimension, del u del n is taken as del u del x in the x direction. So this equation can be further simplified. The last term in the left hand side, this represents the NBC term or the known term. We shift this in the right hand side. Shifting the NBC term to the RHS right hand side, we obtain integration over omega e. So it is w del u del t dx, w del u del t dx plus integration along omega e, w c del u del x dx, w c del u del x dx plus integration over omega e. This is nu into gradient of w into gradient of u. In one dimension, we can write it as nu into del w del x into del u del x dx equals to the source term portion, integration over omega e, w s d omega e plus boundary integral along gamma e, w into nu del u del x dx. So this represents the weak form of the given convection diffusion equation, for example in one dimension. This is the weak form of the convection diffusion equation. So we have considered in one dimension. It can be considered also in multi-dimension by appropriately changing the terms. Then we shall go for the Galerkin formulation. Let us consider Galerkin formulation. For GFEM, we get Wx equals to psi IEx, and we consider the trial solution. The trial solution is considered as u xt equals to summation of uj psi j plus summation of ube psi be, where j equals to 1 to nen, and here b belongs to eta g. Eta g is the set of the Dirichlet or essential boundary nodes. Here nen, it represents the number of nodes per element for a two-noded bar element. We have local nodes 1 and 2. So this is an arbitrary element E, and here our nen equals to 2. Eta g is the set of EBC nodes. So here this subscript B in UB, it represents the boundary nodes. Now this portion left hand side is function of space and time. So certainly the right hand side of the trial solution, this also represents the function of space and time. We separate the terms in such a manner that we consider the degree of freedom to be a function of time and the shape function to be only a function of space. So this we can rearrange as summation over j equals to 1 to nen uj only a function of time, psi j only the function of space, plus summation b belongs to eta g ube. This also we can take only as a function of time or constant, and here psi be only a function of space. So then we can substitute this Galerkin formulations weight function to trial solution. So now we can substitute W equals to psi IE as recommended for Galerkin formulation as well as the trial solution in the above weak form. So plugging in the W equals to psi IE expression or relation and the trial solution in the weak form, we obtain integration over omega e psi IE del t. U is replaced by the trial solution, so it is summation of uj psi j equals to 1 to nen plus summation of b belonging to eta g for u be psi be dx plus integration over omega e psi ie c del x summation of uj psi j equals to 1 to nen plus summation over u be psi be where b belongs to eta g plus integration over omega e for nu del psi ie del x of summation uj psi j plus u be psi be dx j equals to 1 to nen b belongs to eta g equals to integration over omega e. W is replaced by psi ie, source term d omega e or dx plus boundary integral over gamma e psi ie nu del u del x d gamma e. So nu del u del x we can replace by h bar as given by the NBC. So we can simplify this equation further here. Simplifying, we obtain summation over j equals to 1 to nen integration over omega e. The term will be psi ie psi j dx into del uj del t. Psi ie psi j dx into del uj del t. uj del t. This is the first term of the unsteady contribution. Then we have the unsteady EBC contribution. It comes as summation over b belongs to eta g integration over omega e psi ie psi be dx del ube del t. Now we have the convection term. This convection term will be represented as summation over j equals to 1 to nen integration over omega e psi ie into c into del psi j del x uj del psi j del x uj plus summation over j equals to 1 to nen integration over omega e psi ie c psi j del x dx ube plus summation j equals to 1 to nen integration over omega e nu del psi ie del x del psi j del x dx uje plus summation over b belongs to eta g. Here this will be for the EBC portion. So this is b belongs to eta g. So here we have integration over omega e nu del psi ie del x del psi be del x dx ube equals to integration over omega e psi ie s dx plus boundary integral over gamma e psi ie h bar d gamma e. So this represents the specially discretized convection diffusion equation. This is the specially GFEM discretized version of convection diffusion equation. This version is the semi-discrete form of the given strong form. The semi-discrete form represents the ith node ODE in time for element E. So ODE in time at the ith node of eth element. To represent the semi-discrete form in a compact manner, let us introduce the following symbols. Integration over omega e psi ie psi je d omega e equals to mij. This is known as consistent mass matrix. From here we can define the counterpart of consistent mass matrix associated with the time dependent essential boundary conditions. So integration over omega e psi ie psi be dx equals to mibe. Next we have the flow terms. So integration over omega e psi ie c del psi je del x dx. This is equals to cije. This is known as the convection matrix that we have already discussed in the 7th module in conjunction with the first order hyperbolic partial differential equation. Then we have integration over omega e psi ie c del psi be del x dx equals to cibe. So this will be B. Next we have the diffusion terms. Integration over omega e nu del psi ie del x del psi je del x dx equals to dije. This is the diffusion matrix. Next we have integration over omega e nu del psi ie del x del psi be del x dx equals to d ibe. This represents part of the diffusion matrix in association with the essential boundary condition. With the introduction of these symbols, the weak form now may be represented in a very compact manner. For the semi-discrete form, the semi-discrete equation is represented in a compact form as summation over j equals to 1 to nen mije del uje del t. This is the first term, summation over mij del uj del t. So its counterpart for the EBC will be summation over b belongs to eta g m ibe del ube del t. Next we shall have the convection matrix. So this will be summation over j equals to 1 to nen cije uj. The convection matrix is summation over j equals to 1 to nen cije uj. Then its EBC counterpart will be summation over j equals to 1 to nen cibe ube. Then we shall have the diffusion contribution. This will be summation from j equals to 1 to nen dije uj. Its EBC counterpart is b belongs to eta g summation dibe ube. So these are all the left hand side terms. Now in the right hand side we have the source term. This we can represent as integration over omega e psi I e s dx and the NBC portion as boundary integral over gamma e psi ie h bar d gamma e. Now let us define integration over omega e psi ie s equals to fie due to source term and boundary integral over gamma e psi ie h bar d gamma e equals to fie due to NBC. Now these two portions, these are the unsteady term contribution. Next we have the convection term contribution, and in the left hand side we finally have the diffusion term contribution. Now we shift the EBC contributions due to MIBE, CIBE and DIBE to the RHS as known terms to get summation over j equals to 1 to nen mije del uje del t plus summation over j equals to 1 to nen Cij uj plus summation over j equals to 1 to nen for dij uj equals to fie source plus fie nbc minus summation over b belonging to eta g mibe del ube del t minus summation over b belonging to eta g cibe ube. So this will be b belonging to eta g minus summation over b belonging to eta g dibe ube. The entire terms in the right hand side we can represent by a single vector fie. Define fie equals to fie source plus fie due to natural boundary condition minus summation where b belongs to eta g mibe del ube del t minus summation over b belonging to eta g cibe ube minus summation over b belonging to eta g dibe ube. With this definition of all the known terms, the semi-discrete form gets its even simplified compact form. This leads to summation over j equals to 1 to nen mij del uj del t plus summation over j equals to 1 to nen cij uj plus summation over j equals to 1 to nen dij uj equals to fie. This represents the ith node ODE or semi-discrete version in compact form. So here we can write them in the matrix form, and then since uje is a function of time only, we can write summation over j equals to 1 to nen mij duj dt plus summation over j equals to 1 to nen cij uj plus summation over j equals to 1 to nen dij uj equals to fie. In matrix form, we write it at me due dt plus convection matrix ce into ue plus the diffusion matrix de into ue and the RHS load vector fe, where the size of the square matrix is nen by nen. So this is nen by nen. The vectors are nen by 1. So this is nen by nen, nen by 1, and finally the load vector is nen by 1. After performing assembly and implementing the boundary conditions, we can write the final assembled matrix equation system in the semi-discrete form. After assembly of element level me DE, CE, FE, and implementation of boundary conditions, the global semi-discrete equation for 1D convection diffusion equation is given by m du dt plus cu plus ku equals to the load vector. So this is the semi-discrete form. Now the temporal discretization can be performed by using the generalized trapezoidal rule that we have already introduced in the 7th module during the handling of the parabolic partial differential equation. Time integration for the first derivative du dt term can be performed using trapezoidal rule under the finite difference framework. We shall consider the explicit scheme or the forward Euler scheme first. So case 1, explicit or forward Euler scheme. So let P represents number of time steps and delta t equals to size of time step. If delta t tends to infinity, we get a steady state condition. Now, for the explicit scheme, we can write the above generic expression as m u vector at p plus 1 minus u vector at the pth level divided by delta t plus the convection matrix as it is multiplied by the degree of freedom at the known or the pth level plus the diffusion matrix and the degree of freedom again at the known or pth level equals to the load vector at the pth level. Here we treat p plus 1 as unknown level and p as known solutions at the pth level. The assembled mass matrix, assembled convection matrix, diffusion matrix as well as the load vector, they are considered as independent of time. M, C, D and F are independent of time for the problem under consideration. Size of M, C and D, D means K, here it is D, so this is certainly D here. are max q by max q. Max q means the maximum number of equations. So after assembly, how many equations we have in the global system, that is the size of the all matrices M, C and D. So we have max q number of global equations. So this expression we can simplify as mass matrix into the unknown vector of p plus 1 level equals to mass matrix with the known solutions at the pth level plus the load vector at the pth level multiplied with delta t minus the convection matrix and the diffusion matrix added with the known degree of freedom vector multiplied and having the time step delta t. So here this is the unknown part in the left hand side. We have all the known solutions in the right hand side. So entire right hand side is known. So we can find out the unknown quantity by mass lumping or by direct calculation. So this consistent mass matrix, it can be mass lumped. The consistent mass matrix may be row sum lumped for straight forward solutions. Now we illustrate the fully implicit scheme or the implicit Euler scheme. So this represents the space and time discretized algebraic equation system. So the semi-discrete version is space discretized. When it discretized by time integration schemes, we get the fully discretized algebraic equation system. Incidentally, because the governing equation was linear and the boundary conditions are also linear, our matrix equation system at the end, it is also linear. So here we consider case 2, implicit or backward Euler scheme. So here we have m u at p plus 1 minus u at pth level by delta t plus c into u at p plus 1th level plus d into u at p plus 1th level equals to f at p plus 1th level. This we can simplify as m into u at p plus 1th level minus m into u at pth level plus we have the convection matrix C and the diffusion matrix D multiplied with delta t, and we have the unknown degree of freedom vector u at p plus 1th level equals to delta t into the load vector at p plus 1th level. So from here we shift the known and unknown terms to the corresponding sides, then we get the final version as the mass matrix minus delta T into convection matrix plus diffusion matrix into the unknown DOF vector at P plus 1th level equals to delta T into load vector at P plus 1th level plus the mass matrix into the degree of freedom vector at the known or pth level. So here the right hand side is known and the left hand side this is unknown. Now we know that the Crank-Nicholson scheme is found out by taking the average of the forward and the backward difference schemes. So case 3, this is Crank-Nicholson scheme. This is second order accurating time. Order of accuracy is order of delta T whole square. Like the backward Euler scheme, this is also unconditionally stable. So we can find out this from, we have the semi-discrete equation m du dt plus c plus d into the DOF q equals to f. Forward difference gives m into u at p plus 1 minus u at p by delta t plus c plus d u at pth level equals to f at pth level. Then the backward difference gives m into u at p plus 1th level minus u at pth level by delta t plus c plus d into u at p plus 1th level equals to f at p plus 1th level. We take average of these two expressions. Here by adding we get 2 into mass matrix. Then we have the degree of freedom at known level minus the degree of freedom at the, then we have degree of freedom at the unknown level minus degree of freedom at the pth level divided by delta t plus convection matrix plus diffusion matrix multiplied with the known DOF vector plus the unknown DOF vector equals to the load vector at the pth level plus the load vector at the p plus 1th level. So from here we can further simplify m into u at p plus 1 minus u at pth level plus delta t by 2 into c plus d into u at pth level plus u at p plus 1th level equals to delta t by 2 into the load vector at pth level plus the load vector at p plus 1th level. This we can rearrange as m minus delta t by 2 into c plus d u p plus 1 equals to mass matrix into u at pth level minus delta t by 2 into the convection matrix plus the diffusion matrix multiplied with the known DOF vector plus delta t by 2 into f of p plus f of p plus 1. Now the convection matrix and diffusion matrix together we can write as a stiffness matrix representation for compactness. We may write K equals to stiffness matrix equals to C plus D to get a compact form as M plus delta t by 2 into K into the unknown DOF vector equals to mass matrix into known DOF vector minus delta t by 2 into the stiffness matrix multiplied with u at pth level plus delta t by 2 into the load vector at the unknown and the known levels p plus 1. This can be again simplified as mass matrix plus delta t by 2 into the stiffness matrix. Here we have q at p plus 1 equals to mass matrix minus delta t by 2 into stiffness matrix entire multiplied with the known DOF vector plus into f at p plus f at p plus 1th level. So now we have developed the expressions for the forward difference scheme, backward difference scheme and the Crank-Nicholson scheme for the temporal derivative. These are special cases of the trapezoidal rule or the generalized alpha parameter rule. Case 4. Generalized alpha parameter, where alpha lies between 0 and 1. Then we can represent the above algebraic fully discretized equation is expressed as m plus alpha delta t into k multiplied with the unknown DOF vector equals to the mass matrix minus 1 minus alpha delta t into stiffness matrix multiplied with the known DOF vector plus delta t into 1 minus alpha into Fp plus alpha into F at P plus 1th level. Alpha equals to 0. This is for explicit scheme. Alpha equals to 1. This is for implicit scheme. Alpha equals to half. This is for Crank-Nicholson time integration. And alpha equals to 2/3. This is for Galerkin time integration. We have already mentioned that the Galerkin as well as Crank-Nicholson time integration, they are second order accurate, whereas the explicit Euler and implicit Euler, they are both first order accurate. Here there is 1. This term is 1 minus alpha. So in today's class, we have provided space and time discretized version of unsteady convection diffusion equation in one dimension. The unsteady convection diffusion equation contains a convection matrix and a diffusion matrix. For today's class, I recommend the textbooks by Professor T.J.R. Hughes as well as by Professors Donia and Huerta. Thank you very much for attending this lecture.